All right, welcome to the deep dive. Today, we're digging into something pretty fundamental about the newest AI models.
You mean the ones that seem like they're...
Well, thinking.
Exactly. You've seen the names OpenAI, DeepSeek, Claude, those big players. They're often called large reasoning models, LRMs.
Right, because they don't just spit out an answer. They generate this whole thinking process first, like chain of thought, sometimes even trying to self-reflect.
Yeah, it really looks like reasoning, doesn't it?
It absolutely does. And, on the standard tests, math problems, coding challenges, they often do show improvements over models that just give the final answer.
Yeah.
Showing their work, or seeming to, feels like a big step.
But here's the big question, the one buzzing around and what we're diving into. Are they really reasoning? Like, in a flexible way?
Or is it just, incredibly good pattern matching? But maybe still pattern matching at its core.
And tied to that, are the tests we usually use actually giving us the full picture? Do they show the real capabilities and the limits? Exactly. And to get at that, we're looking at a really interesting research paper today. It's called The Illusion of Thinking, understanding the strengths and limitations of reasoning models via the lens of problem complexity.
The illusion of thinking. Wow, okay. They're not pulling any punches with that title.
No, it definitely signals a challenge to the common view.
So if the standard benchmarks aren't quite cutting it, what did these researchers suggest instead? How did they propose getting a better look?
That's the core of their method, using these things called controllable puzzle environments.
Controllable puzzles.
Yeah. So our mission today, using this paper as our guide, is basically to unpack what these models can and can't do when you give them structured problems where you can precisely tweak the difficulty.
Okay, and this is for you listening if you're curious about AI and want to get past the hype, right? To understand the fundamentals a bit better.
Precisely. Getting a clearer picture of the actual strengths and, importantly, the weaknesses.
All right, let's jump in. The paper argues that our usual evaluation methods, like math or coding tests, have blind spots. What are the main issues they point out?
Well, they focus on a couple of key things. First, there's the issue of data contamination. It's a constant headache in AI.
You mean the model might have already seen the test questions or something very similar during training?
Exactly. These things are trained on just unimaginable amounts of internet data. It's almost impossible to guarantee they haven't seen similar problems or even bits of the solutions before.
So when it gets it right, you don't know if it's reasoning or just remembering.
Right. Is it figuring it out now or recalling a pattern? That's the contamination problem. It muddies the waters when you're trying to assess true reasoning ability.
Okay, that makes sense. What's the second issue?
The second one is about transparency, or maybe the lack of it. Standard benchmarks usually just score the final answer.
Even with chain of thought.
Even then, the model might show its steps, but for complex problems, it's incredibly hard to verify if every single one of those steps is logically sound and actually led to the answer.
So the thinking trace could just be plausible sounding text generated alongside an answer it got some other way. Maybe pattern matching again.
It's possible. And crucially, when it fails, it's hard to pinpoint why internally, just from that final output or even the trace. You can't easily debug the reasoning process itself on those complex benchmarks.
Okay, so benchmarks have contamination risks and aren't great for seeing the internal process clearly. How do these controllable puzzles fix that? Why are they better for this job?
Their real strength is well, control. You can precisely manage the difficulty.
How so?
You can systematically increase the complexity, like adding more disks in Tower of Hanoi, or more people needing to cross the river, while the basic rules of the puzzle stay exactly the same.
Okay, consistent rules, just scaled up difficulty.
Precisely. And this setup helps get around data contamination, because you can generate tons of new puzzle variations at different complexity levels. It's much less likely the model saw these exact configurations during training.
So less risk of memorization, and you can precisely dial the difficulty. What else?
Well, these puzzles force the model to use algorithmic reasoning based only on the explicit rules you give it. There's no ambiguity, no relying on fuzzy, real-world knowledge it might have picked up. It has to follow the logic provided.
Right, pure rule application.
And here's the kicker. Because the rules are simple and the state of the puzzle is always clear, you can actually check every single step the model proposes in its thinking process, programmatically.
So you can see exactly where it goes off the rails if it makes a mistake.
Exactly that. You're not just grading the final answer, you're watching its work step by step and can pinpoint the exact moment its logic fails.
That sounds incredibly useful for understanding limitations. What kinds of puzzles did they use?
They use 4 classics: Tower of Hanoi moving disks between pegs.
Okay, yeah.
Checker jumping. Swapping checkers on a line. River crossing puzzles. You know, getting wolves and sheep across without disaster.
Right, those logic puzzles.
And blocks world stacking blocks in a specific target configuration. For each one, they could just ramp up the difficulty by adding more items, disks, checkers, people, blocks.
Got it. A controlled lab for logic. So what happened when they actually tested the models? They compared the LRMs, the thinking ones, against standard models.
Well, they did. And the results were really revealing. They found what they call 3 regimes of complexity. Basically, performance changed dramatically depending on how hard the puzzle was.
3 zones. Okay, what were they?
So first, at low complexity, the really simple versions of the puzzles, something surprising happened.
What was that?
The standard models, the ones not generating thinking steps, were often more accurate. And they used fewer tokens, so they were more efficient.
Huh. So the extra thinking actually got in the way for simple stuff.
It seemed to. Maybe overkill, adding computational costs without benefit, or even introducing errors.
Okay, what about the next regime?
Medium complexity. This is where the LRMs started to shine. That ability to generate intermediate steps, the thinking, seemed to really help navigate these moderately tricky problems. They outperformed the standard models here.
Ah, so the thinking pays off when things get a bit more involved. That makes intuitive sense.
It does. But then came the third regime, high complexity.
And what happened there? Let me guess. The standard models failed.
Well, yes, but so did the LRMs. As the puzzles got really complex, both types of models basically hit a wall. They saw a complete collapse in performance. Accuracy just dropped to 0 or near 0.
Wow, a complete collapse for both. Even the ones designed for reasoning.
Even them. So the thinking helps in that middle zone, but it seems it's either inefficient for easy problems or completely breaks down for the hard ones.
That really complicates the picture, doesn't it? That generating more steps isn't a silver bullet for harder problems.
Absolutely. It challenges that straightforward scaling idea.
Let's focus on that collapse at high complexity. You said accuracy plummeted. Was it a gradual decline or more like falling off a cliff?
The paper's figures show it's often a somewhat gradual decrease as complexity ramps up, but then, yeah, it hits a critical threshold. And beyond that point, performance just tanks.
Yeah.
Very sharply.
A cliff edge, basically.
Pretty much.
Yeah.
For all the LRMs they tested, like Claude 3.7 Sonnet Thinking, DeepSeek R1, O3 Mini the pattern held, accuracy goes from maybe okay-ish to essentially 0 very quickly once that complexity threshold is crossed.
Okay, and what about the amount of thinking? The number of tokens they used in their reasoning process? Did they try harder as the problems got tougher right up to the collapse?
This is where it gets really weird and interesting.
Yeah.
Initially, yes. As problems got harder, moving into that medium complexity zone, the LRMs did generate more thinking tokens, which makes sense. Harder problem, more steps needed, right?
Right, you'd expect more effort.
But as they approached that critical collapse point, that complexity cliff edge, they actually started using fewer thinking tokens.
Wait, they thought less just before they failed completely on the hardest problems, even if they had the token budget to think more.
Exactly. Even with plenty of token budget available, the length of their generated thought process started to shrink as they got close to the collapse threshold for the really hard problems.
That seems backwards. Why would they do that?
The paper suggests this points to a fundamental scaling limitation. It's not that they just run out of space to write down their thoughts. It's like the reasoning process itself, whatever it is, fundamentally falters or gets derailed by the complexity, leading them to produce shorter, ineffective reasoning attempts right when they need longer, more careful ones.
So it's not just running out of steam, it's like the engine seizes up when the load gets too heavy.
That's a good analogy. They curtail their effort just when more effort is needed, suggesting a breakdown in the core reasoning capability relative to complexity.
That's fascinating. And they could actually look inside these shortened, failed thoughts because of the puzzle setup, right? What did the analysis of the intermediate steps show?
Yes, validating every step was crucial. They found clear patterns depending on complexity.
Like what?
For the simple problems, they often found the correct solution path quite early in the thinking process. But then they just keep going, exploring totally wrong paths afterwards.
Seriously? They found the answer and then got lost.
Yeah, the paper calls it overthinking. Found the goal, then wandered off into the weeds, wasting compute.
Okay, inefficient. What about moderate complexity?
There, the pattern often flipped. They'd explore incorrect paths first, and then sometimes, later in the thinking process, they'd stumble onto the correct solution.
So more trial and error, eventually finding the way sometimes.
Kind of. And then for high complexity in that collapse
Let
regime.
me guess. No correct path at all.
Exactly. The generated thought simply didn't contain a correct solution path. The internal process was just wrong or completely failed to make progress.
So it seems like their ability to explore solutions and self-correct is, well, flawed. It's inefficient on easy tasks and just breaks on hard ones.
That's certainly what the analysis of the steps suggests. These inefficiencies and limitations in their search or correction strategies become really apparent when you track them against complexity.
Were there other really surprising findings? Things that challenge what we think these models should be good at?
Yeah, a couple stood out, particularly around what the paper calls exact computation, just following logical steps precisely, and also their consistency.
Okay, give me the most striking example.
For me, it was the Tower of Hanoi experiment, where they actually gave the model the exact algorithm to solve it.
They told it the steps, like move disk from A to B, then C to A.
Explicitly,
Yeah.
step-by-step instructions right there in the prompt. You'd think, okay, now it just needs to follow the recipe. That should be much easier than figuring out the strategy itself.
Yeah, execution should be simpler than invention, so performance showed up.
That's the amazing part, no. Performance didn't really improve significantly, and the collapse at high complexity, it still happened around the same point.
Wow. So even when told exactly what to do, step by step, it still failed on complex versions.
Yes, which is huge. It suggests the limitation isn't just in finding the right strategy, but potentially in the basic ability to reliably execute a sequence of logical operations consistently, especially as the sequence gets long.
A failure of reliable execution, not just planning. That's a really fundamental issue.
It points towards that, yeah. It's about consistently applying the logic over many steps.
What about the consistency between different puzzles? Did they behave similarly across different logic tasks?
Not always. They found some pretty puzzling inconsistencies there, too.
Such as?
Okay, take the Claude model again. On Tower of Hanoi for N10 disks, it could actually manage a fairly long sequence of correct moves they mentioned, around 100 correct steps before it failed. That's quite a long chain of logical actions.
Okay, impressive sequence length there.
But then on the river crossing puzzle with N3 pairs, which, by the way, has a much shorter optimal solution, only about 11 steps, I think the same model failed much, much earlier, after only about 4 correct moves.
Hold on. You could do 100 steps correctly in one puzzle, but only 4 steps in a different, logically simpler puzzle that requires fewer total steps.
Exactly. It could handle the long, complex sequence in Tower of Hanoi N10, but fell apart almost immediately in river crossing N3.
That doesn't sound like a general reasoning ability that applies consistently across different logical structures.
It really doesn't. And the paper speculates why this might happen. It could link back to the training data again.
How so?
Maybe examples of river crossing puzzles with more than, say, 2 pairs and 2 are just incredibly rare online in the stuff these models were trained on.
Ah, so if it hasn't seen that specific type of logical structure frequently in its training data, it struggles to generalize or execute it, even if the logic itself isn't inherently harder than something else it can do.
That's the hypothesis. It suggests performance might still be heavily tied to the patterns and structures present in the training data, rather than a pure, abstract ability to handle any logical task based on its intrinsic complexity.
Which kind of brings us full circle back to that pattern matching versus true reasoning question.
It does indeed. These inconsistencies really feed into that question.
Okay, let's try and wrap this up. If someone's trying to understand what these very impressive thinking AI models are truly capable of, what are the main takeaways from this deep dive based on this paper?
I think the core insights are pretty clear. First, while these LRMs are powerful and the thinking traces look convincing, these controlled puzzle tests show they hit fundamental limits when problems get complex enough. There's a sharp collapse.
Okay, a complexity ceiling.
Second, and maybe more surprising, they seem to struggle with just reliably executing logical steps sequentially, even when you tell them exactly what the steps are. It's not just about finding the plan.
The execution problem. Right.
And third, their performance isn't always consistent across different types of logical tasks, which might suggest, as we just discussed, a continued reliance on patterns learned from training data rather than a truly general reasoning faculty.
So it definitely challenges the narrative that we're just smoothly scaling our way towards artificial general intelligence or robust reasoning just by making models bigger or having them generate more thinking steps.
It really does. This kind of research, using controlled experiments, suggests there might be more fundamental hurdles with current approaches when it comes to reliable, scalable logic, not just, temporary bumps we'll easily overcome with more data.
And for you listening, understanding this is, I think, really important. It helps appreciate the amazing things these models can do. They're genuinely useful, especially in that middle complexity range, perhaps.
Augmenting human work.
But it also gives us a clearer-eyed view of their limitations, what they can't do reliably yet, which helps us use them better, be more critical of their outputs, and just have a more realistic perspective on where AI is actually at.
Definitely. And that leads us to a final question, really, the one the paper leaves us mulling over. Given these demonstrated failures, this collapse on structured tasks that need precise logic, does this reveal a fundamental barrier? Are current approaches inherently limited in achieving true generalizable reasoning? Or are these just growing pains? Are these limitations temporary hurdles that bigger scale, more data, maybe slightly different architectures will eventually overcome?
That's the big question, isn't it? Fundamental wall or temporary roadblock. What do you think after hearing about these findings? Something to consider.